So when you look at carrier movement, carrier change and move and sort of basically transport, at one level you're going to be asking some very particular questions. In particular, you're going to be asking what carriers are going to get moved by various external fields, external forces, and what sort of things are you going to have does that sort of diffuse, basically have carriers shifting from high concentrations to low concentrations. And we talk about this transport as drift, where it's actually movement of carriers due to an external field, and diffusion, which is movement of carriers due to sort of pushing against concentration gradients. In other words, making things more generally flat. And the sort of transport you see with this is very, very similar to, in terms of carriers, really makes this look like fluids. And it's really sort of a typical fluid transport. And so that's kind of, you'd see a lot of similarities. If we're talking about transport of fluids, we'd have similar terms with similar fields with similar ideas. Now, when you're doing this, we're making certain assumptions that, basically on average, things are not, very high electric fields. We're not doing things that radically change the distribution functions, things that are typically sort of staying away from what are typically the higher field effects, where the distribution functions of the carriers matter a lot. If you don't do that, then you're basically talking about sort of electrons and holes as sort of acting like two different charged component fluids that are interacting together. And in fact, you actually get places where you get most of these things. There's sort of looking at ions in a charged fluid, you'll see something similar, although not quite the same. And so this is how we would talk about things. And so we'll typically start with a conversation of drift, which is typically movement of carriers due to an external field. For when we typically talk about semiconductors, you're talking about electric field almost always. It could be magnetic field, it could be a change due to temperature. It could be a number of other things, but typically you're going to see electric field, which is the gradient of the potential. And so you might see if I have a band diagram, and again, every time we talk about semiconductor structures, we're going to have a band diagram, both conduction band and valence band. And so we'll have the hole sitting in the valence band and the electron sitting in the conduction band. And obviously a gap in between that is dependent on the material. It turns out if you actually look at it for drift, you get a very straightforward kind of approach here where you say, well, the current density is going to be related to, well, a couple things. What is that electric field? It'll in fact be proportional to that electric field. That's the first thing for these sort of low field approaches. So the higher the electric field, the higher amount of current I'll have because they'll be moving faster. There'll be a faster velocity. In fact, the velocity of the carriers is typically going to be this mobility term mu times that electric field. So that actually gives you a real sense of the speed of the carriers. There's always going to be Q, which is just a unit charge, because again, in the end, we're dealing with either a unit charge of electron or a unit charge of a hole. They have the same size, a different sign. So this is a signless quantity. This is always positive when we say Q. It's 1.6 times 10 to the minus 19th. And then it also turns out the number of electrons is proportional to the number of carriers, or that current is proportional to the number of carriers available. And so this proportionality works fairly straightforward. Now remember that current is always defined in the direction of positive charge. And this kind of gets interesting when you talk about, well, what's the current for, electrons, right? Because you go, wait, I see the same value and no difference in the sign. Well, this is where you kind of want to watch what's going on in the band structure because, the holes will move in a particular direction. They're a positive charge, and they'll move in that with the electric field in that direction. What'll happen for the electrons is they'll move in the opposite direction with the opposite charge. So so a negative times a negative gives you a positive, and so in the end, it works out reasonably well. So drift is like one of the main starting things that you would work with there. And it has basically a nice sort of product of various terms when you look at it. The other side is asking the question of diffusion. And now you're talking about moving carriers away from, if I have a large number of them, I want to move to something lesser. Well, if I have a concentration gradient, which means there's not many here and there's some here, obviously there's a derivative. And I want to move opposite of the direction of the derivative. Okay, so for holes, you can say, okay, if I have a strong derivative, that means I want to move in the opposite direction, so I'm going to get a negative sign related to that derivative. And then there's just basically a coefficient, which is called a diffusion coefficient. And that would be related, again, to particular materials, much the same way that mobility for electrons and holes are going to be sitting there. Interestingly enough, electrons have a different sign. Again, remember, you're moving a negative charge rather than a positive charge. So it turns out, you're going to kind of move these things as a result of a concentration gradient. And they're going to move in the same direction. They're going to move away from the concentration gradient. But the signs are different because of the different charges. And this gets interesting because in a real practical sense, you really have in most systems drift and diffusion current. And that actually gets to be fun because you have both drift, because I may have changes in the band structure, and this is a good indication that there's an electric field there. I'll also have concentration of carriers in different places. And that may also be found by saying what is a Fermi level, what is a quasi-Fermi level, and then I can kind of go, oh, I definitely have charge carriers there. And so actually the band diagram is one way to picture what's happening. Another way to be able to discuss what's happening then is to say, well, what is the actual current density that I'm getting there in various structures? Again, even here, see, there's a band diagram because of the electric field shift. And in fact, if it's a nice linear shift, this is what's actually called Ohm's law. These are actually formulations of Ohm's law. In this particular case, so I would actually have to go, I've got concentration levels, I've got electric fields, and you might go, well, does this happen often? And it's like, yeah, most of the time, particularly when I have some sort of barrier structure, like a p-n junction or MOS transistors, or even, say, biological channels or other sorts of charge carrying medium. And so all of these concepts are extremely important to kind of analyzing so many of the device physics properties, particularly at sort of the low field and sort of slightly moderate field kinds of behavior. And this is where most of our fundamental device models come from.